Welcome to today's Explainer. I am absolutely thrilled you're here because right now we are dusting off a 50-year-old cold case in particle physics. Scientists working over at CERN's Large Hadron Collider are seeing what might just be the strongest hints ever of physics beyond, well, beyond everything we thought we knew. We're literally talking about rewriting the rulebook that governs the fundamental building blocks of our universe. So let's just dive right into it.
To understand why this is a massive deal, we have to acknowledge a glaring hole in human knowledge. For half a century, our universal rulebook has been incredibly successful, but it's visibly incomplete. Just look at that 25% chunk right there. That represents dark matter. It's invisible, it's currently unmeasured, but it makes up a huge portion of our universe, and our current theories simply cannot explain it. They also can't explain gravity. So we know for a fact there are massive missing chapters in our understanding, and scientists are aggressively hunting for them.
Here is our case file for today. First, the 50-year-old rulebook. Then, the giant crack finder. Followed by the rare penguin decay, 1 in 16,000. And finally, rewriting the laws of physics.
Section 1. The 50-year-old rulebook.
Okay, so this brings us to the Standard Model. This has been the reigning heavyweight champion of particle physics for 50 years. It's an incredibly elegant framework built on two of the 20th century's absolute biggest breakthroughs, quantum mechanics and Einstein's special relativity. It explains fundamental particles, the absolute basic building blocks of matter that just can't be divided any further. For decades, physicists have thrown everything they have at the Standard Model. They've subjected it to insanely rigorous testing. And for 50 years, even though everyone knows it completely ignores gravity and dark matter, nobody could find a single crack in its math. That is, until potentially right now.
Section 2. The Giant Crack Finder.
Meet the Giant Crack Finder, the Large Hadron Collider, or LHC, over at CERN in Geneva. It's a massive particle accelerator sitting in a 27-kilometer-long circular tunnel buried deep beneath the French-Swiss border. Its whole purpose? To intentionally try and break the Standard Model. It does this by accelerating beams of protons in opposite directions and just violently smashing them together. By digging through the microscopic debris of these collisions, scientists are looking for hints of undiscovered physics. Our focus today zeroes in on findings from two specific experiments housed down there, the LHCb and the CMS.
Section 3. The rare penguin decay.
Now you've got to love the names physicists come up with. A penguin decay. It's a term for a specific, incredibly rare transformation of short-lived subatomic particles. And yeah, if you use a little imagination, the arrangement of the particles on a diagram actually kind of looks like a penguin. But scientifically, what's crucial here is that watching this decay lets researchers study how one type of fundamental particle, a beauty quark, transforms into a strange quark. It gives us this really unique window into seeing particles morph into entirely new forms.
Let's map out this chaotic little quantum event step by step. Step 1, our beauty quark enters the scene packed inside a particle called a B-meson. Step 2, an electroweak transformation kicks off. That's the decay itself. Step 3, emerging from all this, we get a strange quark plus a kaon, a pion, and 2 muons. At the LHCb experiment, scientists are painstakingly measuring the exact angles and energies of these newly produced particles as they fly apart. They're looking for indirect observations. It's actually a lot like how radioactivity was discovered 80 whole years before anyone directly saw the W bosons that caused it. They are hunting for the invisible influence of heavy, entirely undiscovered particles messing with this decay.
But here is the real kicker. 1 in a million. According to the unbelievably precise math of the Standard Model, for every 1 million B-mesons, only a single one is supposed to decay in this specific penguin manner. Because it is so vanishingly rare, it acts like a hypersensitive tripwire for the hidden influences of brand new particles. And the LHCb team, well, they found that their real-world measurements of these decays simply do not match up with what the Standard Model predicted.
Section 4. 1 in 16,000.
This brings us to a quote straight from the research accepted in physical review letters. The data shows, and I quote, "a tension of 4 standard deviations from the expectations of the Standard Model." Now, in science speak, tension is basically a highly polite way of saying the theoretical prediction and the hard physical reality are throwing punches at each other.
Let's translate that 4 standard deviations into something a bit more concrete. It means that after crunching all the uncertainties, there is only a 1 in 16,000 chance that a random statistical fluctuation this extreme would happen if the Standard Model were perfectly correct. Just let that sink in for a second. A 1 in 16,000 chance. It is highly unlikely that this is just some fluke in the data.
And this illustrates brilliantly exactly where the scientific community is stuck right now. 4 sigma, our 1 in 16,000 chance, is incredibly compelling evidence. But physics is notoriously rigorous. It stops just shy of science's absolute gold standard for claiming a definitive discovery, which is 5 sigma. 5 standard deviations means there's a 1 in 1.7 million chance of a fluke. So we aren't at 5 sigma just yet, but the evidence is rapidly piling up.
Plus, what makes this whole narrative even crazier is that it's not just one isolated experiment seeing this. An entirely independent setup at the LHC, called CMS, published their own data earlier in 2025. And while their results aren't quite as precise as the LHCb data yet, they line up perfectly with the findings. The case against the standard model is literally getting stronger by the day.
Section 5. Rewriting the laws of physics.
So, if the standard model is wrong, what on earth is the right answer? Well, let's line up our unseen culprits. Physicists are throwing around a wide range of new theories. The anomalies could be caused by very heavy, completely undiscovered particles exerting some unseen quantum pull on the decays. Other theories point to leptoquarks. These are wild hypothetical particles that would actually unite 2 totally different types of matter, leptons and quarks. Or we might just be looking at heavier analogs, essentially massive hidden cousins of the particles we already know.
But hey, every good detective story needs a plot twist, right? Enter the charming penguins. Yes, another fantastic name. These are a set of processes that do already exist inside the standard model, but their effects on the decay are notoriously tricky to calculate. So, some scientists are naturally asking, are these charming penguins just interfering and messing with the data? Well, recent estimates, combining theory with the LHCb experimental data, suggest these charming penguins simply aren't powerful enough to cause the massive anomalies we're seeing. The standard model is genuinely sweating trying to explain this away.
So how do we finally solve the case and hit that ultimate 5 sigma gold standard? It comes down to pure volume. Between 2011 and 2018, the LHC recorded around 650 billion BMES in decays. By 2026, that massive data set will have tripled. And looking further out to planned upgrades in the 2030s, they are going to accrue a dataset 15 times larger than that. The sheer mountain of upcoming data will eventually allow scientists to say, definitively, whether or not we are officially unlocking a brand new understanding of the universe at its most elementary level.
And that leaves us with this final thought. We started by looking at that massive 25% of the universe hidden in a way in dark matter. If the foundational 50-year-old laws of our universe are truly cracking and about to be completely rewritten by heavy new particles or leptoquarks, if the fundamental laws of our universe are about to be rewritten, what else are we missing in the dark? It is an incredibly exciting time for science. I hope this explainer helped you grasp the mind-blowing detective work happening right now under the French-Swiss border. Keep learning, keep questioning, and I'll catch you in the next explainer.